only mode.
Okay, good afternoon, everybody. Thanks for joining us for today's webinar. We're going through, and this is going to be the 8th one of the series. It's hard to believe for all of you who have been with us back from January or February, whenever we started, that there's only one more left after this, and you might be thankful at this stage, kind of hard to say. But for the next hour and a half or so, we're going to go through and talk about diagnosing and addressing inefficient HVAC operations. This one's going to get in a little bit technical, and we're going to go through some interesting examples and I hope some very specific information. It's going to be looking a little bit more at just operation and how it is that we can achieve preservation while trying to achieve sustainability and energy savings in mechanical systems at the same time. For those of you who haven't joined us in the past, my name is Jeremy Linden. I'm the Senior Preservation Environment Specialist here at IPI, and I'm proud to note that we apparently have promoted Chris from ably assisting to skillfully assisting today. Who's to say next month we might find out that he's professionally assisting or expertly assisting. It's hard to say. But yeah, Chris is in the background. So if you hear any sneezing or coughing or anything else, we'll just blame him as we go through. As always, if there's any questions or you need some technical support, Lauren's contact information is there on the slide. The contact and call-in numbers, if you're having any audio problems, are there below as well. And again, if there are questions going through, and I hope there are at least a few, I'll do my best to make sure that we leave some time for questions and discussions at the end of the session today. But any questions that you have, feel free to send in through the question box over on the GoToWebinar control panel. Chris will be seeing those first, and he'll be getting back in touch with folks during the webinar as he can. And some of those that we receive in will be the ones that I address and we talk about here at the end of the session today. Again, this is the 3rd series of workshops and webinars that we've done in this particular topic, and thank you as always to the National Endowment for the Humanities through their Education and Training Grant Program for funding this series, not only for the webinars that we're doing currently up through next month, but also for funding the 5 on-site seminars that we were able to do last year and earlier this spring. And I hope all of you at the end of this will send in your evaluations and reviews of the program, especially here as we start winding down. National Endowment for the Humanities really does appreciate hearing in our report specifically what it is that people thought of this process and what it is that you may have learned from it and whether or not it's something that we should continue doing on into the future, not only for NEH's input but also for our own. The webinars in the Sustainability series is really designed to try and make sure that we can achieve some better understanding of how we can balance both preservation of collections, but also look at the sustainability goal. How is it that we can reduce energy consumption in mechanical systems, but also just in buildings in general as we move forward? And what we're trying to achieve here, our bottom line goal is really to try and put out some practical guidelines and some information and examples that folks can use for managing and reducing risk to collections as they go about trying to find these energy-saving measures in their buildings, whether it's through mechanical systems or just looking at overall energy usage in a particular facility or building, or in many cases, as we talked about just a couple months ago, looking at buildings without mechanical systems and how it is that we can try to achieve better preservation environments or better preservation conditions even without mechanical intervention. And today's presentation is really going to harken back a little bit to what we talked about back in January or February for those of you that remember. And we're going to go through and just talk about some of the standards and where they came from very quickly, just as a means of introduction. And from there, we're really going to dive in and talk about mechanization. We're going to talk about how it is that we intervene with mechanical systems and HVAC in modern buildings primarily, not so much in historic buildings this week, but in modern buildings primarily, and what it is that we can do to try and find that best combination of preservation and energy savings when it comes to building operation. So that note at the bottom really does come into play, and just as forewarning for those of you who weren't already aware, that we're really talking about medium to large institutions here that have modern HVAC capabilities. And we're going to dive right into sort of that building physics and more particularly some of the engineering that goes on. So to review and go back again, as I said, a few months to what we've talked about over the course of this entire series, we need to make sure that we're defining correctly what it is that we're trying to achieve when it comes down to what it is that we want the preservation environment to be. And to put it in succinct terms, or at least as succinct as I'm capable of, A flatline 70-50 environment, 70 degrees, 50% relative humidity, is 99 times out of 100 when it comes to preservation not our goal. It's not anymore what it is that we're trying to achieve. When we're looking at what is best for preservation, and also as we look at year-round conditions throughout much of the United States, Canada, and elsewhere in the world, it's also not often the best condition from a flatline perspective for long-term sustainability and long-term energy savings. And that even though that 70-50 or flatline condition was never officially established as a standard when we're looking at preservation for libraries, archives, and museums, quite often that under that sort of stated range, that 70-50 plus or minus just a little bit, is something that was generally accepted throughout the field. And it's something that as time has gone on, not only has it been accepted within the world of collections and preservation, but coming at it from the architect and engineer perspective, it's also been accepted as part of our design bottom line. And that's something that we want to talk about a little bit today as we go through. You know, what it really comes down to and what we have to be careful about is that maintaining that 70-50 condition is not always necessarily better for preservation. We lose a lot of opportunities in there in that very tight control, as we talked about with the equilibration work a couple months ago. That tight control is not always necessary when it comes to preservation, but beyond that, that can be extremely expensive when we look at different operating types or different operations over the course of a year for various environments. And as we went through and started building more and more, started constructing more and more buildings and cultural institutions to these standards, and assumed that we wanted very tight control with not a lot of fluctuation in temperature and relative humidity, and that oftentimes that, you know, if we looked at it in the past, say 20, 25 years ago, and assumed that that human comfort condition, that 70 degrees, 50% was best for what was for the collection, for what the collection needed, then we wound up finding ourselves in situations where we have a relatively new building that is only equipped or only designed to achieve this very limited type of operation. You know, finding out that you're limited in terms of dehumidification to roughly 70 degrees and 50% RH, or a 50-degree dew point, and finding out that, you know, by and large the system is operated constantly and trying to achieve these very tight conditions and very tight standards. When we start looking into it and realizing how much money we're spending on energy and what it costs us in terms of fossil fuel consumption, more often than not, you know, part of the problem comes right back to, well, what is it that we expect? What is it that we're trying to create? And what we're finding, what we're learning as we move forward, is that as we understand better what the material decay pattern is of different types of materials and how it is that we have to worry about degradation over time, we're finding out that those cooler temperatures and moderate relative humidities that we've talked about here for the last few months, we realize that those goals, that setting that type of condition is different than what many of our buildings and systems were originally designed to do. So we're stuck, or we're left with trying to create these more appropriate preservation conditions, oftentimes with equipment and design buildings that weren't necessarily meant to achieve that. So it's always a little bit of an experiment in creativity. You know, how is it that we can get there? How is it that we can make something do a better condition when it wasn't meant to do that to begin with? And really what we're looking at is trying to balance preservation, trying to balance what it is that we do in terms of maintaining preservation environments and, you know, trying to slow the rate of decay of different types of collections materials. But we're doing that balanced as a balanced risk management approach. You know, we're trying to make sure that we don't introduce conditions or that we manage conditions in terms of ranges or fluctuations within what we understand through research to be safe levels, and making sure as we do that that we're trying to achieve the best the best energy consumption possible. And in order to get there, this is really the audience that we need to listen in today, is that it means that we have to have a team-based approach. It means that we have to come at this not just with collections or preservation expertise, but that we also have to come at it in direct communication and in very good sharing of knowledge and working together with both facilities management professionals, you know, whether they be our building engineers or our architects, but also looking at it too with our administration and being able to understand from the perspective of the larger institution or the larger organization what the priorities need to be and what the goals in terms of balancing preservation and balancing operating costs need to look like. And finding those sweet spots or finding those points where everything cooperates and works together takes the input of all of our colleagues as well as not, in addition to just us as collections professionals. So the goals are pretty straightforward. We're looking to reduce the risk, but first and foremost, and that doesn't mean one thing that we have to be careful of here is that while we want to achieve improvements in energy efficiency, the key is that we don't ever do that at the cost of preservation. We don't want to achieve energy savings or reduce our costs in terms of building operation and do that, unfortunately, let's say to the detriment of collections preservation. You know, everything that we've talked about over the last few months and everything that we're going to cover today is first and foremost with the goal of either improving preservation or at least not changing the current preservation conditions that you may have. Any energy saving strategies or energy saving operations that we might be able to identify are meant to be put in place or meant to be tested in order to be achieved without changing that preservation quality. And I would certainly recommend or certainly encourage everyone that's listening in to take that as your first and foremost goal. You know, try to improve energy usage or improve energy savings, but not at the cost of preservation. And finally, as we've talked about before, this optimization goal and making sure that when it comes to the environment, we're trying to achieve the best preservation environment that our own system and our own building is capable of creating, and that we do that with the least possible consumption of energy. But we're faced, the reality is we're faced with just what happens every day. You know, the standards that are being redefined as we speak in a couple of different professional organizations in terms of what the preservation conditions may be, the standards such as they are, when we go back and look at those and how to achieve them, we're still faced with this absolute reality that is, you know, in real life, excess energy consumption when we're going through and looking at how systems actually perform is absolutely common. In fact, I can safely say that I don't think I've ever walked into a single building that was not using, in one way or another, using more energy than was necessary to create its preservation environment. But the other part of that is that, you know, when we think about that excess energy consumption, it doesn't self-announce. It doesn't jump up and say, hey, look at me, I'm using way more energy or way more fuel or way more money than is necessary to create the environment that you want. More often than not, what we run into is that the environment, in the end, the temperature and the relative humidity in the space look exactly like what it is that the institution expects, exactly what people are looking for. But it's in the background, it's the details of how the air is worked on, of what each component is doing and performing that really lead you to find out and go, wait a minute, we're not doing this as efficiently as we could, or we're wasting energy in this particular operation that is unnecessary at the end of the day when we're looking at the preservation goal. So moving in and thinking about how it is that we actually go about this, we talked last month about looking and trying to document mechanical systems and finding out what it is that we have. We're going to start off this month with going in and figuring out, well, what data do we actually need? Where do we have to put data loggers? What do we have to find out in terms of being able to start diagnosing some of what's going on? And the first step, you know, this is something that we advocate beyond just relying on the building management system, although using the BMS and using those sensor points is certainly a part of this process. But looking for that sort of independent check, that independent information to make sure that you have multiple points of data and making sure that you have checks and balances across one another, we advocate using data loggers within mechanical systems at each of those locations where a component or the mechanical system can actually do work to the air. And what it is we're looking for these comparison points. We want to find out as we put a data logger in the return air and in the outside air blend, you know, when we start looking at the mixed air condition where those two air paths are going to come together, how much outside air are we using and how much return air are we using? There are several different equations that you can run in order to find out what your balance is and find out if you're using more outside air than might be necessary. And at the same time, you want to know that what is that mixed air condition as it moves through the filters. When it hits the cooling coil, how much work is that cooling coil actually doing? So we might want a data logger after the cooled air location as well. This diagram just shows a couple of examples of very typical places where we might find data loggers within the airstream. Oftentimes we're looking, you know, first and foremost for the return air condition that comes back from the space to understand what it is that the collection may have felt or a blend of that. But we're also looking to see what the condition of the air that's being sent into the space. And that might be a logger that we call the supply air over in this location, or even further downstream if we have some sort of terminal equipment, as we discussed last month, in that ductwork before it actually goes into the space. And then in the interim, we're looking again to find out, what is the type of work that we've done to that air as it's moved through the loop. And we're going from the return air, maybe we have outside air over here, a preheating coil. What might that mixed air condition be between the return air and that outside air stream? How much work does the cooling coil do, and how much work does the heating coil do? And as we start to pull all of that data over time and we gather it in and bring it up on a graph or start to run through and work on the analysis portion of it, not only can we find just how much work is being done, if we look at a mixed air condition and then look at the cooled air condition, we can figure out exactly how many degrees of cooling it is, both sensible and latent, both in terms of sensible temperature and looking at dehumidification, that cooling coil is actually doing. And once we know that number of degrees worth of work, we can back it out and start thinking about how many BTUs of energy that might equate. But we can find, so using that data, we can find the energy usage, but we can also think about what it is that we know or how it is that we know the equipment should be running. And we can use that data and use those graphs to start to detect any different equipment faults or inefficiencies that may be happening. And we'll show a couple of examples of that as we get a little bit further in. But it's just to say, this is that good combination or that good opportunity to cooperate and work with facility staff and talk as both the collection side and as the equipment or facility side about what it is that we expect these units to be doing and how each of those components should arguably be performing as we go through that process. And when we get something that looks like this at the end of the day, multiple different plots on a graph, and we realize that, all right, if I follow my return air, this nice kind of greenish bluish color here, well, that stays fairly steady. When the return air comes in, it gets mixed with outside air to create the mixed air condition. So that mixed air is now cooler than the return air. That tells us that we're using definitely some outside air, and presumably that the outside air condition is a little bit cooler down here, depending on where we're at. So we have a mixed air condition, and now we're going to say, all right, after the mixed air, we go to the cooled air, and here we are. Not only do we see that the cooled air on a normal basis might be creating, let's call it 52 degrees when it's turned on, but we also see that we have this pattern in the cooled air plot. And that tells us, well, maybe there's a shutdown going on, or there's some other factor of control that's being put in here. And as we start to dive into this operation a little bit more closely, we want to find out what's causing this particular swing in air condition at that cooling coil. Finally, after the air gets cooled down to this condition of 52 degrees, we send it out and it hits a heating coil. And before we send it out to the space, we find out that it's going to get heated back up to about, give or take 64, 65 degrees. And at that point, we know what the supply air condition is that's going into the space. That tells us exactly what the air temperature is that we need in order to find and achieve our final set point condition out where the collection is stored or out in the public area. So being able to follow those paths and think about what each of those plots means and how much work is being done from one step to the next in terms of how many degrees is happening is a good way of beginning this diagnostic process and being able to think about whether or not we're operating as efficiently as we want to. Now, once we have those data loggers within the mechanical system, we can go back, and this actually moves a little bit deeper into the documentation phase. I think we introduced it a little bit last month. But we can go back in a little bit deeper and start looking at documenting what the system itself is actually capable of and what it is that we're working with. So, the goal here is really going to be to find a combination of different tools or different documentation techniques that we can use to go through and make sure that we understand exactly what the system is supposed to be doing, how it was designed, what the goal should be or what its normal operation should be, and we can weigh or we can compare what it currently does against what it was initially meant to do. We can do that using zone maps and cartoons and schematic drawings to go through and, first of all, first and foremost, identify which mechanical system is actually serving which space. Do we have situations where we have a mixed-use zone and we're trying to figure out, all right, who all receives some of this air? We want to make sure that we know what different components we have within the air handler. We talked about that a lot last month in terms of how do you find or how do you identify a cooling coil or a heating coil or a filter. Understanding a little bit more what the design capability is of the system, we'll look at that specifically, but also understanding, look, what is it that the unit is supposed to do? What is it in terms of actual control? And looking at that sequence of operation, what is it that's supposed to occur? Now these zone maps, you can do these in a number of different ways, and a number of institutions that I've worked with have already had these prepared. Others, and if you're one of the ones that hasn't worked on this or hasn't identified this yet, it's a good place to start. You pull out a set of mechanical drawings and you find the room or the space where the actual air handler might be, and you just begin tracing ductwork. You look at the supply air and look to see, all right, well, where does that go out into the building and what rooms does it serve? And you start to find all of a sudden that, well, here we go, this zone that happens to be served by A3 is the name of the mechanical unit. Well, some of A3's air goes up here, but some of it also goes over here. And did we realize that? And in this particular physical zone, here's my wall surrounding this particular perimeter. As we start looking within that room, we realize all of a sudden, even though this is just one physical space, now I've got 1, 2, 3, 4 different air handling units that are serving a portion of that physical space. So as you walk through the room, on one particular spot, we may be in A3, and over here we might be looking at D2 or F2W or whichever mechanical system that might be. And that's critical to understand, because if we start having problems in terms of meeting set point or what the conditions might be in a particular zone or particular space, we need to know which mechanical system we have to go back to and start looking at more closely in order to find out what might be going wrong, in order to find out what needs to be, what adjustments have to happen. We want to make sure that we're actually doing it to the right system, to the right HVAC unit, as opposed to going in and changing conditions or set points on a unit that has nothing to do with our storage area. Then trust me, that's happened. So we start with the zone maps, and then we dive in a little bit closer and we look at the cartoons. And by the way, if you're curious about this, there's a lot more information about this in the workbook and the guidebook that goes along with this series. There's also a lot more information about this online at ipisustainability.org. But as we go through and we move from the zones into the cartoons, I think we discussed this a little bit last month, but we're going to use those cartoons to detail exactly which components we have and what the airflow is throughout the building. So where does it go, or what does it hit within that pattern of the loop as it goes from one mechanical system out to a number of different spaces. In those cartoons, as we said, we're going to identify those different system components and make sure that as we're thinking about operation, we know where the filters live and we know where the cooling coil and the heating coil are, what that arrangement is, where, if we have any, where does humidification occur, and also what those moving parts are. Remember, where is it that the dampers sit, and what type of control do we have over top of those. And then moving into this overall diagram to just realize what that relationship is, sort of on a macro scale, as we start to look at the overall building, understanding, well, if we know where the mechanical system is and we know these red circles are where we place data loggers, this is where our data within the mechanical system is coming from. But we also go out to the spaces that get served by that mechanical system, and, well, here's a data logger that I have in the space, and here's another one. This room that's, maybe down the hall or next door, we've got a couple of data loggers in there as well. And as we start to get these diagrams going, we understand what those physical relationships are between the different spaces, but also the mechanical system that serves them. And the data that we look at as we go in and start working with it within the graphs is going to make far more sense in terms of understanding why certain things occur. If that data logger starts to show a warm temperature, well, is it because it's awfully close to the lighting and the light's giving off some heat, and that's what we're picking up. As we go through, we look at this and realize I need to start writing some of this information down. It's really critical that we have this in one location where everyone can share it. That it's not sitting, shall we say, within the context of the mechanical drawings or within the context of the building drawings, where the only person with regular or easy access to it might be the facilities staff. The goal here is really, when we're working within this team environment, is to make sure that this critical data about how the building is expected to run and what the capability of different mechanical systems might be, that information is stored or retrieved and placed in a location where it's accessible by the entire team. So this is just one example of what we use. We will share this, a link to this particular tool in the follow-up email. But we want to use this checklist to go through and figure out, what type of different components do we have and what are they designed to do. Some of that information is going to come from the air handling unit schedule that will sit within the mechanical design drawings for the particular unit that you're looking at or for your building. Now this could be a little bit tricky. Your design drawings may go back to 1965 or they may only be 4 or 5 years old. But as we go through and start looking at these AHU schedules, we realize this is where some of that critical information about how the system actually runs sits. It's where it lives. And as we go through and find out, well, here are my entering conditions and leaving conditions off of the cooling coil, and there's water temperature, but in this particular case, if I want to know what that coil is designed to do, well, what's the leaving air condition? If we find out that the leaving air dry bulb is 51 degrees and the wet bulb condition, this is going back to the psychrometric chart, but the wet bulb condition is 50.5 degrees, well, we can go in and run a calculation to find out and realize on the psychrometric chart that the dew point temperature for those two conditions is 50 degrees. So this cooling coil, talk about going back to those unintentional standards, but this cooling coil that serves a storage space within an institution is actually only meant to create a 50-degree dew point for us, which means that any set point conditions, any temperature, any preservation goals that we set are going to be specifically and very distinctly influenced by what that dehumidification capacity is. With a 50-degree dew point, we're going to have a hard time keeping cool temperatures in there in order to slow the rate of chemical decay. Now the other part that plays into this, and the other part that we can spend some time on in terms of that documentation process, is looking at the building management system and understanding what the different points of control are and what we have available to us. Not just what the set points are for various components, how is it that the cooling coil runs, or how does the set point condition for the supply air, or how does supply air get decided upon? Is that something that is determined by the condition in the space, or is that something that is a set condition leaving the heating coil at all times? But also, where are the sensors that determine how the mechanical system actually runs? Are we working off of return air sensors or supply air sensors, or sensors that are out in the space or maybe an average of multiple spaces throughout a zone? We want to be able to look at it and say, all right, if we have valve positions available to us for different coils, whether they be cooling coils or heating coils, on a hot summer day, if we go in and look at that BMS, well, if we're trying to dehumidify, then we might expect to see the cooling coil valve 100% open. And if we don't, that's a good time to start asking questions about, well, could we do better with dehumidification if it was? And also looking at damper positions, not just in terms of outside air and return air, but also thinking about the potential for face and bypass. And where is it that the air is being routed to, and how are the dampers that decide that? How are they controlled? What makes up that decision? Or they just sit in the same spot all the time? So, it was a dark and stormy evening, and Lucy walked in, and she realized that she'd forgotten everything that she'd ever learned about mechanical systems inefficiencies, and she wanted to know where okay, you get the point. I won't go into that too far, and although it would be fun to do a radio serial sometime on this topic, talk to Patty about that. Maybe we can script one of those. But thinking about it, the inefficiencies, what do we have to think about, and what do we have to find out? There are really 4 big questions. First of all, is we know we use energy when we have a mechanical system. Where does it go, right? Which components use it, how much of it? And we need to find out, is there something that's happening that doesn't have to? Is there some way that we're being inefficient in our operation that, as we said before, just isn't self-announced? We don't find it because it doesn't manifest as being broken. There are a number of different cases where we might find out that the system is actually working against itself. We may be cooling far more than necessary, and that then creates far more need to heat. And we'll talk about an example like that in just a couple of minutes. And at the bottom line, really, it's just looking for whether or not we're using more energy than we have to. And I think I mentioned this maybe last month, but this is kind of an overall view, and this is just a baseline or a guideline to keep in mind. These numbers actually come from Peter Herzog, a partner of ours that we've worked with for a number of years here at IPI. And over the course of his 30 or 40 years of looking at mechanical systems and buildings and energy usage, he started pulling together some numbers and trying to figure out, well, just how much energy does each of these typical components tend to use? Because we have our expectations and kind of our, shall we say, assumptions as we move into this. And what Peter found over time really is that if we look at the individual components, roughly 20% of our annual energy cost when it comes to the mechanical system is being used at the air handling fan, whether it's a supply fan or a return fan. Another 30% of that annual cost is being used by the cooling coil, with 40% over the course of a year being used at a heating coil. Now, in a place like, shall we say, let's guess Georgia or Washington, D.C., or even here in Rochester, New York, although Rochester wouldn't be as much of a surprise, but oftentimes if you tell folks that the heating coil uses more energy than the cooling coil, it'll cause them to pause for a second and say, well, that doesn't make sense because it's cooling and dehumidifying that is the most expensive operation. Well, that's true, but if we're dehumidifying via a subcooling reheat process, we talked about that last month also, but if we're dehumidifying, we realize that we also have to reheat if we are subcooling. And that means in many operations or in many buildings, that heating coil is doing some amount of work all year round, regardless of the season, when the cooling coil really is only doing its job for those months where we need to specifically cool or dehumidify. When we're looking at humidifiers and talking about how much energy goes into that, it's usually a relatively small portion of the overall pie, if you will. And the one that always fascinates me, and it's kind of an interesting thought and, certainly a strategic, shall we say, concern or a strategic issue that needs to be talked about, is this number where you start looking at lighting. And lighting, at least in Peter's experience, and this also applies to my experience as well, where lighting is really about 6% of your total annual energy cost when you start looking at these mechanical operations within a building. And the reason that that's critical or interesting, is really that when we think about where we start to make energy improvements, or where it is that we oftentimes put a lot of our sustainability focus, one of the things that jumps up immediately for a lot of institutions, maybe it's because we think it's the low-hanging fruit, is lighting upgrades. There are a lot of projects out there where, first and foremost, let's change over from fluorescents to LEDs. Let's get the work on this, and we're going to see a significant energy impact, and we're also going to see some preservation impact because the LEDs aren't going to, have as many issues in terms of UV light as the fluorescent might have. Let's see what we can do here. Well, what it comes down to is that lighting is actually a rather small part of the overall energy picture. And while it's important to go about and make those changes or make those improvements, I would make the argument that you don't want to do that at the cost or at the exclusion of looking at the overall mechanical operation of the system as a whole. Those lighting improvements are certainly critical and definitely important and excellent if we can achieve them, but don't think that you're getting all of the, shall we say, necessary improvements or optimization if we only look at that lighting component. Now, a couple of different, we're going to start getting into just some broad suggestions here, and how to think about, well, what type of equipment do I have, and how might I think about trying to reduce some energy use. The first step, just thinking about fan consumption and how it is that fans use energy. One thing, there are a lot of institutions out there that have variable speed drives installed on supply or return air fans for mechanical systems, and a variable speed drive really is just a dimmer switch for a fan motor. As you increase the speed of the fan, it moves faster and circulates more air. And as we take this dimmer switch, if you will, or take the variable speed drive and slow the fan down, it means that we're decreasing the amount of air that goes over the coils and goes out into the space. And what we found in research is really that reduction of air quantity, especially throughout and when we start looking at seasonal operation, is certainly a good possibility for trying to reduce energy consumption, but still oftentimes maintain the preservation conditions that we have in spaces. There's no set fast amount that you can adjust the quantity of air that moves through, but between shutdown experimentation and setback experimentation, looking at fan speed, we've come to realize that oftentimes the amount of air that we send to the spaces has been over-designed or overestimated, or at least conservatively estimated, when we started looking at the initial design of a system in the building. So the possibility here is to just start experimenting with that reduced fan speed when possible, especially during unoccupied hours, or even at night, even if there's just less occupation in the building. If there's less occupation, oftentimes there's going to be less energy load. And just an example of this, one way to think about it, is if we look, this particular graph is plotting the energy usage off of a supply air fan, and it's measuring, in this case, the amperage that the fan is consuming. And we'll just take a look, follow me through here for a minute, but here we are in weekdays. We use an average of 68 amps as we go through during occupied hours. Notice here's my unoccupied hours here at night. And then on the weekends, notice that we've slowed that fan down a little bit. We've taken it from 68 amps down to 62.5. We've reduced its controller operation by roughly 10% when we look at this. And that's oftentimes something that as a facilities manager or even as an administrator, we might look at and say, well, that's a good model of trying to reduce energy use, right? We're putting in nighttime setbacks. We're slowing the fan down on the weekend when there's less occupation. We slow down the fan a little bit compared to the weekday, and we're saving energy. Well, it's absolutely true. I won't argue with that. But what I would argue, and I think the case to keep in mind here, is simply that we're missing an opportunity. This is a classic case of underutilization. As we start looking at this particular pattern and say, well, all right, we are saving energy, but are we saving as much as we could? And one place to sort of think through this or talk about it over is when we start to get into a fan power curve. And hopefully a few of you that are listening in have run into this in the past, and if not, here's an introduction for everybody else. But what it comes down to is that the fan power curve isn't a linear relationship. As we start to reduce fan power, well, the good news is that we can maintain an awful lot of our, shall we say, total airflow in terms of how much air that we're sending out to the space. But what that does in terms of the horsepower that we actually use or the energy that we use is fairly significant. So here's our example here where we just reduced that operation of the fan from the day, let me go back up, here's a weekday operation, and down to the weekend operation. We reduced it by not quite 10%, right? So here we are. We've backed off on that fan speed by 10%, down to about 92. And as we do that, notice as we drop down this curve, by reducing that airflow by 10%, we've also managed to save almost a quarter of our total energy. Now that's a pretty good relationship, right? Most of us would say, well, 90% of airflow going through a space on a number of days, anytime where we're not at a peak day or the hottest and wettest day of the year in terms of summer conditions, 92% of total airflow is going to be more than enough to still achieve what's going on in the space. This comes back to experimentation, but oftentimes it holds true. Well, if I can run at 90% of total capacity but save 25% of my energy, that's not bad. Well, what if I can go in a little bit further and let's say I find out that during the night or in wintertime that if I send 50% of the total air into the space, I can still maintain conditions. Well, here we are. We'll take it a little bit further down, and if I get down and run that fan at 50% and send 50% of the total air in, well, we've just saved 90% of the total energy consumption. That's a pretty darn good payback. If we can run a space with 50% of the total quantity of air and still maintain conditions and save 90% of the energy that it takes in order to do that, that's kind of a no-brainer. Now, it's awfully hard. Many VFDs won't actually dial down quite that far. You still have a limit in terms of how they can operate. But it's this idea that you want to consider. I would argue that there are a number of spaces out there, especially in terms of storage, where for a good percentage of the year, you could probably reduce that total airflow down to 80% or 75%. And notice that if we did that, maybe we're only looking now at this stage at roughly, maybe we're saving 60% of the total energy that we were using before. So consider this as one possibility as you're thinking through and talking about, are we being, shall we say, less efficient than we could? We oftentimes assume that just because a system was designed a particular way, that that's the way it always has to run. What we tend to forget is that systems are designed for worst-case scenarios. They're designed to operate at these peak conditions in the summertime and in the wintertime. And in order to do that, they have to do the maximum amount of cooling or heating, but also send the maximum amount of air into the space in order to carry away the energy that's being imparted through the building and through the load. So for those days when it's not a peak condition, where it's not the absolute hottest or the absolute coldest, we don't need the system to do 100% of what it's capable of. Oftentimes we can reduce that percentage of operation by some quantity and still achieve exactly what we're looking for in terms of space conditions. When we're thinking about cooling and dehumidification, the two things that really come into play here are what is the leaving air set point off of the cooling coil? In other words, what is the temperature the coil is trying to achieve? But the other part, and this is one that we have a lot of control over, and oftentimes we don't think about it very carefully, is a huge driver of this entire process is how much outside air we bring into the system. The outside, I think we've talked about this in the past, but outside air is really our primary culprit when it comes to introducing moisture load into a building. You know, most of the moisture and most of the water that we deal with in terms of having to dehumidify, or the lack thereof in terms of having to humidify, is directly related to what we bring in through the mechanical system on purpose in a modern building with a modern HVAC system. And if we bring in too much of that air, then it just increases the amount of work that we have to do. So if we're talking about storage scenarios, or even if we're talking about patterns of occupation in a space that would normally house people, the goal, or something to think about, is really to try and minimize the quantity of outside air whenever possible. You know, if there isn't anyone in the building between the hours of 6 at night and 6 o'clock in the morning, then outside air is, for all intents and purposes, unnecessary. The critical with outside air, by and large, when it comes to preservation, is about keeping people healthy and about keeping people happy. You know, there's certainly, in a, shall we say, a film storage only scenario, I think there are some discussions to be had about how much outside air is necessary. But in a lot of our library and archive storage facilities, the less outside air that we use, the better off we are, both in terms of preservation and in terms of energy. As we start looking at seasonal conditions or for cold climates and thinking about heating and reheating, you know, this is where it comes down to, and this is something that we have to say very, very carefully. You know, we've talked about in the past that cooler is certainly better in terms of preservation for the vast majority of materials that we have in our cultural institutions. And the key here is that we want to be able to maintain as cool as possible as long as we can keep that moderate relative humidity condition. We've talked about that in the past. I won't really go into detail there. But, you know, the operation, shall we say, the functional operation of this is that if you live in a cool climate, don't overheat the space, especially if it's not occupied by people regularly. If it's primarily for storage, keep the temperature down. And, you know, as long as you can maintain that band of safe relative humidity between 30 and 35% and 55%, then make it as cold as you can go. Oftentimes, as long as you're not moving into a situation where you have to mechanically cool, the goal here is to try and get the space to run passively, to try and reduce temperature so that you're not heating it mechanically, you're not expending energy there, but also so that you're not introducing mechanical cooling. Let the space go as low as the outdoor environment in the building will let it be. Now, as we start to drop that temperature, the other thing that happens, especially in cold and dry climates, whether it's seasonal or all the time, is we drop that temperature, the relative humidity is going to start to go up. And if you're in a cold, dry environment, especially, you know, looking at most of the entire northern United States in the wintertime and a large portion of Canada, parts of Europe, as you go through and start thinking about that, as we drop temperature, relative humidity is going to go up. And now all of a sudden we're also reducing the amount of humidification that we might have to do in a space. Or if we don't have any humidification, we're bringing the relative humidity up to a safer range. So that drop in temperature works in two ways, both as a temperature benefit, but also as both as an energy benefit, but also as a preservation benefit in terms of both relative humidity and slowing down the rate of chemical decay. Humidification, you don't oftentimes, you know, you run into in far fewer locations. This is more significant when we look at northern or arid climates over the course of a year. You know, but the key here is, again, start thinking about what this range of safe relative humidities is. And this moves away from that 70-50 rule that, you know, has been kind of floating over our heads for the last 3 decades or so. And start thinking about what the safe ranges are for the materials that you have in your collection. You know, we've talked about that by and large, for a large number of materials, these might range between 30 and 35% on the low end and 55% on the upper end in the summertime. You know, but take advantage of that range. You know, try to make sure that in the wintertime, for most materials, there's really no need or no necessity to humidify all the way to 50% or 55% relative humidity. And if your collection is of the type that you can manage at 30 or 35%, do so. It's going to be a lot easier to control mechanically, and it's also going to reduce the cost of the energy that you're using as you go through. Lighting is a tricky one. You know, you could probably do an entire session just on looking at lighting and sustainability and how we should and shouldn't operate it. Maybe we need to add that to the list to do one of these days. But especially in storage areas, you know, this is one that never ceases to amaze me. There are a number of instances where we've walked in and realized that the room is closed, nobody's in there, all the staff are working in a different part of the building. The only stuff that's in there is collections material. There's no need to see anything on a regular basis unless there's a body in the room. And yet you open up the door and all the lights are turned on. And when that happens, you know, we kind of joke about it here, but we like to say that we pay for lights twice, right? We pay for it in terms of the energy that it takes to create the light in the fixture itself, but we also pay for it because that light gives off heat. And every time, for every bit of heat that fixture gives off, the mechanical system has to account for that. It either has to cool it or it has to bring in outside air in order to try and remove the energy that the lighting is giving off. So, you know, the purpose of lighting is to make sure that if we need to see something that we can. But when we look at a photo like this and realize that we've got a room full of compact storage and there's only one aisle that you can see anything in at any given time, does every fixture in the entire room need to be turned on? Well, the answer is no. If nobody's in there, none of them need to be turned on. And if there is someone in there, then maybe we're better off with a banked control where you can go through and say, all right, I need to work in this quadrant of the room or this quarter of the section area, of the shelving area. You know, start thinking about creative lighting control to make sure that you're not using more energy in that scenario than we need to. And moving beyond just kind of these big picture, big level ones, you know, let's dive in a little bit to the components specifically within the mechanical system. Yeah, and one big one that stands out, and it's because dehumidification, you know, by and large, no matter how we do it, is quite expensive. You know, subcooling and reheating, that process, we've talked about it in the past, where we subcool the air at the cooling coil in order to achieve the dew point that we need. And then we reheat it in order to achieve the proper supply air temperature condition, as well as the appropriate relative humidity to go into the space. You know, this is something that is only necessary at certain times of the year. And now maybe in some climates it's necessary to do year-round, but if you look at it, oftentimes it's not always the same amount of energy or the same amount of subcooling and reheating that you have to do all year-round. So this is one where there are a lot of opportunities oftentimes to find some savings, to achieve some efficiency, some better efficiency. You know, one example here, and this is just a classic one that you run into a lot, especially in buildings where there's a lot going on and maybe they're understaffed, especially from the facilities perspective. It's hard to keep track of everything that's happening with the system throughout the course of the year, is where we get into situations of this unnecessary subcool and reheat. If you look at the plot on the graph down below, notice the date range at the bottom, that we're looking at January of 2011. And I'll tell you right now that this data comes from a site in Minnesota. Now, Minnesota in January has no need for dehumidification at all. The amount of outside air, or the amount of moisture that's available from the outside air is microscopic at best. And when we start talking about, you know, okay, efficiency and operation, we look at these at this particular condition, we realize now, here's the space temp. Well, as the space temp goes back through the loop and back to the unit, what's the first thing that we do? Well, it hits the cooling coil, and it gets cooled all the way down to 45 degrees in the middle of winter, when there's nothing to dehumidify out of that air. So first we dehumidify, or we cool all the way to 45 degrees. Here's my subcooling that should happen in summer. And then as the air moves downstream and hits the heating coil, we reheat it back up to 62 degrees before we then send it back out to the space. So in this particular example, we're doing, give or take, you know, almost 26, 27 degrees worth of cooling, and, you know, look at it, maybe another almost 20 degrees worth of reheating, when all we really needed to do was an initial 10 degrees worth of cooling to send it back out to the space, and we would have been perfectly fine. That reheat coil actually didn't need to do anything at all. Apparently there is a heat load in this space. We need to supply air cooler than what we take back out. But we could have saved all of this energy by simply cooling it down to 62 degrees and sending it back out. So this is a good example where, because the system has been programmed to dehumidify, that scheduling, or looking at the logic control on that operation, is saying, well, there's no difference between summer and winter. And in this circumstance, we're going to subcool and reheat even in January and waste all this energy that is truly not doing anything for us. Now, another part that comes up in this, and this is a little bit tougher to achieve. It takes certainly paying attention, but it's not an insignificant deal. We talked about, you know, just a couple of minutes ago about how these systems are designed for peak operation. And this is sort of normal operation for a mechanical system that's going to subcool and reheat on a peak day. Now, it's 90 degrees outside. Here we are over here at the outside air. And we're bringing in 10% of that total volume and blending it here with 70 degrees of return air. So in order to take that mixed air condition and get it down to our dew point that we need out in the space, we're going to do 27 degrees worth of work here at the cooling coil. We're going to drop that temp by 27 degrees. And over here at the heating coil, we're going to increase it, heat it back up by 15 degrees in order to get the right supply air condition to send out to the space and achieve that particular preservation goal. Now, that's on a 90-degree day. 90-degree day, if it's that peak operation, if it's that peak condition, maybe we hit that 4 or 5 times a summer, which means that the rest of the time, and especially in shoulder seasons, we've got a day that doesn't look like 90 degrees, but more often, maybe something closer to 75 or even 80 degrees. But let's use the 75-degree example real quick. And this is what happens if we use this flatline operation standard. We say, you know what, I want it to be 70 degrees at 41% in this room all the time. I don't want it to move around. I don't want those conditions to change. Well, that system in a part load scenario, if it's still trying to achieve that particular temperature and relative humidity goal, here's what's going to happen. You bring in the cooler air, you mix it with return air. So now we've got cooler air going into the cooling coil, which means that we have to do a little bit less work to adhere to the cooling coil. That's good news, right? We're not using as much energy as we did up here. The bad news is that because it's not as hot outside, there's not as much heat gain in the room, right? We had 10 degrees on a 90-degree day, but only 5 degrees on the 75-degree day. And that means that if we only have 5 degrees of heat gain in the space, that we don't have to send the air in as cold as we did in the past, right? We needed to send it in at 60 degrees on a 90-degree day. On that 75-degree day, maybe we only need 65 degrees. What happens then is if we still do that same amount of work here at the cooling coil to achieve that dew point, guess what? We've just added 5 degrees worth of work or 5 degrees worth of energy that our heating coil now has to do on a cooler day outside. I hope everybody's going, boy, that doesn't make any sense at all. You think about it, you realize, okay, well, why are we doing that? We're still trying to maintain that condition, but in order to do so, we have to send in warmer supply air. Well, to get that warmer supply air condition, this heating coil has to do more work because the subcooling, the cooling coil, always does the same thing. So here we are. We've just gone from a really hot day and only using, give or take, about 42 degrees worth of total energy at these two coils. Now it's cooler outside on a 75-degree day, and now we're using 45.5 degrees worth of energy. Whoops, right? So let's look at a better option. Well, move away from that flatline requirement, right? If it's cooler outside, then now this is a storage scenario, not necessarily an occupied scenario, so there are other factors involved here. But if it's cooler outside, ask yourself, can we maintain a slightly cooler condition within the space? If I'm willing to say, you know what, 70 degrees, well, I can drop that back to 65 degrees and 49% RH and actually have a better preservation condition, a slower rate of chemical decay. What does that do? What happens? Well, now I'm blending 65-degree air with 75-degree outside air, and it means that that cooler mixed air condition equals less work at the cooling coil, less work to achieve the dew point that I'm looking for. Notice we're still doing the same 45-degree dew point. Lost my cursor. But now, because I only have to maintain 65 in the space, I'm back to my 60-degree supply air temperature, and in order to get to 60 degrees, that heating coil only has to do 15 degrees worth of work, which means now if I start comparing and looking at the overall energy picture in the preservation picture of this particular scenario, we had one option up at the top, that part load option A, where on a 75-degree day, we were doing the same amount of preservation, but we were using more energy, right? If we use this part load option B and we change that space condition, we allow ourselves to be flexible in terms of temp and the relative humidity that's being held, but maintain that same dew point condition, notice that now I can get an 18% better preservation quality, right? A slower rate of chemical decay for 17% less energy at the cooling coil and 25% less energy at the reheat coil. Win-win, win, all the way across the board. These are things to think about. These systems are not designed to run, well, let me take that back. The systems oftentimes are designed, and when they're installed, meant to run at 100 miles an hour, 24 hours a day, 7 days a week, 365 days a year. That's what's expected of them. But what we're learning is we start to think about preservation and what the space needs. And as we start to think about, well, what is the environment that we live in, we don't always have to go 100 miles an hour, and we don't always have to go 24 hours a day. Maybe what we can do is back that off. Maybe we only have to go 60 miles an hour. Maybe we can slow down that fan speed. And maybe, instead of running 24 hours a day, we can drop it back a little. And also, when possible, when the outside dictates, maybe we can get better conditions in the space for less money. Now, I wanted to put a picture of the video game Pitfall up there because that's what that word always brings to mind for anybody who is a child of the 80s and used to play the old Atari games. But what happens oftentimes when we have the best intentions and we're going in and thinking, you know what, I'm going to save some energy, or worst case scenario, and this is not to pick on administration, but oftentimes administrations will, put down that blanket mandate of, you know what, we need to save energy, we're using too much energy on cooling. So we're putting across, a blanket statement that instead of cooling to 72 degrees in a space, we're going to cool down to, or we're only going to cool to 75 degrees in a particular space. We're going to change that set point, increase the space temperature, and we're going to save energy. Let's talk about what can go wrong when we do that, okay? Now this is standard design operation. This is a space that is meant to have a dew point of 45 degrees. Here we are over here. That's going to give us that preservation index of 58. That's our preservation quality in terms of the rate of chemical decay. And in order to do that on a 90-degree day, here we go. Here's the process. We're going to have to cool that mixed air condition by 22.5 degrees, reheat it up by 11 degrees in order to get the right amount of the right supply air condition going into the space. And here are the numbers that we wind up with, right? This is how much energy we do for cooling and heating in order to achieve that. Total in this scenario of about 33 degrees worth of work, give or take. Now, here we are. This is where we go in and say, all right, we're going to save energy, right? Instead of doing a 65-degree temperature, we're going to make this a 70-degree temperature in the space. And by bringing the temperature up, we're going to bite the bullet on preservation. Sorry, guys. Sorry, all of you conservators and all you preservation folks out there. The collection's going to decay faster, but we're saving energy, and that's the plan, right? Well, that was the plan, and it didn't quite work out that way, right? Because the only thing we did was we changed the set point in the space. We didn't change what the cooling coil is doing. The cooling coil still thinks we have to dehumidify to 45 degrees. That's what it's told to do. I do this all the time. And if I'm creating a 45-degree condition, leaving that cooling coil, well, now I've got warmer air at 70 degrees blended with the 90 degrees coming in. So guess what? I just used more cooling energy in order to achieve my dew point. Not only that, because we raised the space temperature. Well, remember, in a subcool reheat scenario, if we want the temperature in the space to go up, that means we have to spend more at the heating coil in order to achieve the right supply air temperature to go out. So the end result of what was supposed to be an energy-saving initiative by warming the space up in the summertime is that, well, we did warm the space up, and yeah, we certainly did go through and try to, well, we screwed up, we messed up the preservation, it's now faster than it was. But guess what? We didn't save any energy. We actually used quite a bit more energy, both at the cooling coil and at the heating coil. So if we're talking about changing set point conditions in spaces, we have to think very, very carefully about whether we're simply changing the space set point temperature or whether we're telling the system to do something entirely different when it comes to the dehumidification aspect of operation. Now, all right, well, here's the other thing that we can do, right? I guess where we screwed up was that we kept the cooling coil operation exactly the same. We said we were going to keep that at 45 degrees, so darn it, if we want to save energy, we're going to have to raise both the temperature and the dew point set point coming off of the cooling coil. So the space temperature, yep, we're going to raise it up to 70 degrees. And that cooling coil, we're going to warm that up too so that we're doing, we're only doing a 50-degree dew point now. And I'm sorry, the bad news is the preservation is going to be even worse. But we're saving energy, and that's the key here, right? I'm practicing for a role in play later on. And, gosh darn it, we're going to save energy, and, well, preservation just has to go by the wayside. Well, yeah, whoops. Start going back through and running the numbers, right? We've got warmer air coming back, blending with 90 degrees. And now, even though we're only doing 50 degrees, here we are. We're doing 22 degrees worth of cooling to achieve that 50-degree dew point. But still, in order to get to 70 degrees, we have to add another 12 degrees worth of reheat to get it up to the supply air temperature that we have to have. What happens? We just wrecked our preservation, and we didn't save 1 iota of energy over what we originally did at a 65-degree space condition. All right, we're still trying. We're working on this. Somewhere along the line, we're going to figure out how to save energy, right? Let's give it one more shot. Here we go. All right. This isn't going to work everywhere, but it might work in a library or archive storage area, especially in the summertime. And here's an option, right? If we still do that 45-degree dew point, oftentimes the best way to save energy when it comes to summer operation in a subcool and reheat system is to ask ourselves whether or not we can lower the space temperature in order to do less reheat. So if we look at it and say, all right, I've got a library and archive collection, and you know, there aren't a lot of metal components in here. I'm comfortable at 58% relative humidity. You know, it's not great, but it's pretty good. And notice, well, I've run the numbers on dew point calculator, and if I do 60 degrees and 58% RH, I wind up with the same preservation index or the same rate of chemical decay that I did when I was back there earlier at 65 degrees and 49% RH. All right, so moot point. So we're going to go back through and say, all right, well, if we get into the energy scenario, what actually happens? All right, I've got cool air coming back. I dropped it back to 60 degrees, mixed air condition. All right, I'm still doing 18 degrees worth of cooling. There's my 45-degree dew point. But notice now that because my temperature is significantly lower, the amount of reheat that I have to do is correspondingly less. So now, in order to get this same level of preservation, that same 58 preservation index rating, that same rate of chemical decay, instead of up here originally, the original scenario, keep losing the cursor, sorry guys, instead of doing that 33 degrees worth of total energy work at the cooling coil and heating coil, I can achieve that cool temperature at a higher relative humidity, albeit, and that's something that would have to be looked at in terms of what materials are actually stored in the space. But I can achieve that cooler temperature for now only about 23 degrees worth of work. So, and this, this is where it often comes in and says, well, that's certainly not what we expected to happen. It's not something that we assumed going in. That you mean we can reduce the temperature in the space, maintain the same preservation quality in terms of at least the chemical rate of decay, and save money? Well, in this particular circumstance, when we're looking at summer conditions, yeah, it's possible. It's thinking about these different options and not just assuming that warmer temperatures in the space will always equate to energy savings. As the example shows out, or hope plays out, shows you that it doesn't necessarily work that way. Now, we're going to go in here a little bit and talk about seasonal operation. It's something that a lot of us throughout the world are dealing with, both in the northern and the southern hemispheres. Not sure if anybody's with us from overseas today, but if you are, thanks for joining in, and hopefully it's not 2 a.m. wherever you're at right now. These are a couple of options just to keep in mind, and this, I know this example is very specific, but I always put it in there because I find a lot of situations where once upon a time at the initial design or the initial installation of a mechanical system, the engineers were thinking ahead and saying, you know what, maybe we can achieve some energy savings by using a face and bypass operation. The face and bypass is basically where you don't send all the full 100% quantity of the air. You don't send all the air over top of one of the coils. That's the face is the amount of air that goes over top of the cooling coil in this particular instance. So here we are at the cooling coil, and this would be the face route. But the bypass damper, that bypass route, allows us to send some of that air around the coil and go by it and use that air, and here's the key, use that air on the other side of the cooling coil as free reheat. In other words, we warm up this cooled air condition before it ever hits the heating coil. This is a good option in terms of trying to save a little bit of energy here at the heating coil. The trick is finding the balance point in terms of how much air should we think about bypassing in different conditions. And this is something that you have to experiment with. Oftentimes when you walk into face and bypass operations, they're run according to a particular set point condition or a mixed air condition before the heating coil, or they're run according to oftentimes just a manual setting. Well, this looked like the right amount of air bypass, so we set it there. But we're looking for that sweet spot, right? We're looking for that sweet spot where the amount of blend or the amount of bypass air is just enough to try and reduce that heating operation as far as possible. Now, there are a couple of tricks in here and there are a couple of catches. The first one is that this really works best when we're not using a lot of outside air, because anytime that we use bypass, we bypass air around the cooling coil. If we have a large quantity of outside air coming into the system, then that means that part of the air is going to go by and never get dehumidified. What we work with in this particular scenario is saying, you know what, if there's moisture coming through, then the goal, sort of the theory behind this is, if the moisture is coming through, some of it's going to get caught here at the cooling coil in the first pass and get dehumidified. Some's going to go by, but it's going to blend, come back through the system, and on the next pass through the system, well, some of that air that we missed the first time around, we're going to catch it the second time around. Lost the cursor again. We're going to catch it the second time around, and we're going to dehumidify it on that pass. So the key is that you have to be able to do more dehumidification than the amount of moisture that you're pulling into the system. But here's that blend, right? And notice that this is keeping the same set point condition out in the space, 65 degrees at 50% relative humidity. If we send 100% of the air over that cooling coil and cool it all down to 45 degrees, then here's the amount of work we have to do. There's our cooling energy, and here's the amount of reheat in order to achieve that condition in the space. But notice as we start bypassing some of this air and changing these blends, that means now that if we only send 80% of that air over the face of the cooling coil, this blending condition on the other side between that 45 degrees, 80% of that, and 20% of 67.5 degrees, well, that means this mixed air, this cooled condition blended, is going to wind up at 49.5 degrees. We get the same condition out in the space, but it reduces the amount of cooling we have to do, and it also reduces the amount of reheat that we have to do. And we can keep taking this further and further and further. And in terms of energy savings or practicality, we may choose to stop here or stop here in real life. But we realize that if we keep tinkering and adjusting these face and bypass dampers, that our sweet spot is that if we send 44% of the total air volume over the cooling coil, and we allow that to blend with the 67.5 degrees air that is bypassed on the other side, that we wind up with a 56-degree mixed air condition on the other side of the cooling coil that matches exactly the supply air condition that we need to send out to the space, which means now I get the exact same temperature and set point condition in the room as what I had even in this scenario. But instead of using 33, 34 degrees worth of total energy at these coils in order to achieve that, now I'm using about 12 degrees worth of cooling energy here at the coil, and my reheat is now free because I found the right blend of those conditions. And if I continue recirculating air at those conditions, then I'm eventually going to reach and achieve this dew point of 45 degree, or this 46-degree dew point in space, because I'll catch some of that moisture every time it comes back around in the system. So that's kind of a high-level experimentation, but it's meant just as an example of if you have this type of, shall we say, air path arrangement within the mechanical system through a face and bypass arrangement, don't just take it for granted that whatever those dampers are set at is exactly the right blend or exactly the right quantity of air moving around. You can experiment with those conditions and experiment with that quantity of air that is bypassed to try and find what that sweet spot is. And the key is to have data loggers in place out in the space so that as you're adjusting this amount of air that goes over the face of the cooling coil, you can see as you're making these changes what the result is in the space, how it is that the space condition responds. Seasonal conditions also, we talk about this a lot, especially in New York, up in Rochester. If it's the middle of winter and you've got a storage scenario, there's next to no reason to heat that up to 70 degrees if there aren't any people in there. And this is one that we've run into just in a couple of specific cases lately. But the reality is if you're in a cold environment, whether seasonal or all the time, think very carefully about what temperature you actually need in the space, because as we discussed before, with lower temperature, we can reduce that rate of chemical decay, but we can also save some significant energy when we look at it. So taking it from option A, which is assuming a 70-degree flatline space temp in the wintertime, well, here we are at 70 degrees and 35% RH. Now, if we go down to option B and take a look, well, what's the impact of 65 degrees? What if we drop the temperature by 5 degrees? One note I will tell you, notice that the relative humidity is the same. This particular example assumes that the humidifier is going to continue maintaining a 35% relative humidity in each of these examples. But at 65 degrees, the humidifier is going to be able to save a little bit of energy too. Now, from option A to option B, if we drop that temperature by 5 degrees, what it comes out to is, well, here we are. We don't have to do as much work at the heating coil now. only 13.5 degrees compared to 15 degrees, which means we saved 12% on our heating. But even more important, by dropping that by 5 degrees and maintaining that exact same relative humidity, we just improved our preservation index by 46%. We went from a 58 PI up to an 85 PI, and we just improved preservation for less energy. And we can take it even further, right? Let's say you are in an occupied space. Maybe the lowest condition people can typically work in for an extended amount of time, and this takes some willingness on their part, is about 60 degrees. 60 degrees in a storage space that's unoccupied is fairly easy to put in place oftentimes. And if we can do that and reduce that from 70 degrees in the wintertime down to 60 degrees in the wintertime, here's how it works out, right? We were doing 15 degrees worth of cooling at the heat, or worth of heating at the heating coil. Now we only need to do 12 degrees. We just saved 20% of our total heating energy by dropping that temperature, but we almost have doubled our preservation quality. In other words, the collection is going to last roughly twice as long in those conditions as it did at this 70-degree condition in the wintertime that was costing us 20% more money. So think about that carefully if you've got storage sites or storage conditions in wintertime that are still running at a 70-degree Fahrenheit set point condition. There are oftentimes a lot of opportunities to drop that temperature and see benefit in both preservation and energy. Now, this is research that we've done here at IPI over the course of the last 4 or 5 years, and this is one that I would certainly advocate for a lot of spaces that you can experiment with this and think about it. And that's using system shutdowns, especially during unoccupied hours, as a means to save energy without compromising preservation. And I think this graph kind of says it all. This is one particular example. And when we're looking at this situation, these spikes or these fluctuations in the green line, which is the supply air condition, show the shutdown occurring, right? We have day and night conditions in the supply air. But as we look at the space condition in this particular circumstance, there's very little fluctuation as a result of this shutdown. You see maybe not even a half degree as a result of that. Now, the variables we have to think about in here, essentially what's going to cause the space to go out of set point or out of range when we start to turn our mechanical system off. If we live in a really hot climate, this is a lot harder to do. Although I will say that we experimented and tested it in Birmingham, Alabama, and we could still achieve shutdowns in the summertime after some experimentation. We had to think about how much time the system could be turned off and how much fluctuation in the space was acceptable. Now, storage types, stacks, high-density individual rooms can play into this as well. The more material you have in the space, the more that material will act as something of a heat sink. And as you turn off the system, the thermal mass of the material that is stored in the space can actually run its own environment for limited periods of time. And that was actually shown to be true as part of our equilibration research also. If we've got AHUs that serve the space, we need to know which ones to turn off or make sure that the entire zone is working the same way. And if we have a zone that has to do with people or an occupied zone or a multi-use zone, we have to think carefully about what it is that we're turning off and whether or not people are still in those spaces when we're looking at shutdowns. Interior and exterior wall exposure, obviously spaces that are away from the exterior portions of the building certainly won't see as much load or as much fluctuation on system shutdown, and also keeping in mind human occupation and comfort. But what we're looking for and what we really want to watch is, first of all, what is the amount of fluctuation we see, how much, and does the collection respond to it? One thing that we found out, we'll talk about this in a second, is that those equilibration rates that we talked about a few months back tell us that short-term fluctuations of a small enough degree in temperature and relative humidity really mean nothing to the overall rate of decay for the collection. We want to make sure that when we turn the system off and when we turn it back on, that we recover to the set point for the space. We don't want to see ourselves losing condition in the space because of the shutdown. We want to make sure that if we were at 72 degrees when we turned it off, or if we were at 65 degrees when we turned it off, when we turn it on the next day, it ought to be able to get back to that 65 degrees. And the other part, this is a question that we got an awful lot throughout the research, is, well, when we turn the system on the next day, do you use more energy trying to catch up to the condition that you may have lost overnight? Right? If we lost 2 degrees in space temperature overnight when we turn the system off, does that mechanical system then have to use more energy the next day in order to catch up and get those 2 degrees back? And the short answer really is, in most circumstances, no. A lot of these systems are designed to run at one speed, as we said, roughly 100 miles an hour. So when you turn it on the next day, it just does the same thing it did the day before, although it might take a little bit longer for the space to come back to its set point condition. Normally what we saw is that spaces were coming back to its set point condition within about an hour to 2 hours of starting up the next day. Now the one exception is that in there is if you're using a refrigerant-based or a DX system, direct expansion. If you're using a DX system, those units are of a nature that they typically will cycle in operation. And what you find then is if it starts to cycle more often or for longer periods of time, then you can start to use more energy than what was used without the shutdown. But even in those circumstances, when we started running the numbers and looking at the actual energy consumption, what we found is that the shutdown, when the system started up the next day, that the unit might use roughly between 15 and 20% more energy for a limited amount of time in order to catch up to that set point condition, which means that from the overnight perspective, if you're only losing 15 to 20% of your total energy that you saved overnight and still coming out 80 to 85% ahead, that's worthwhile. And another factor in here is that from our studies and looking at it, there was very little equipment risk in terms of turning these on and off at night. There's more information on that, and we certainly, if you're curious about that, we have more information available on that research. Benefits here, potentially in preservation, right? If we can cool things down, especially at night or for extended hours on a system shutdown in the right seasons, especially in the wintertime, then we can have some impact on the rate of chemical decay, although that might be relatively small. But the bigger one here really is looking at energy savings. There's arguably no better way to save energy than to just turn the entire mechanical system off. And if we can do that for 8 hours a day, or roughly 1/3 of the day, then we can oftentimes save, and we've seen numbers that vary from site to site, but in most cases you save at least 25% on a shutdown, and oftentimes you're looking at somewhere between 30 and 40%, looking at total annual energy savings with an 8-hour shutdown at night. Now the other thing about shutdowns to keep in mind is that they can be of whatever length that you want, and any length that the system is turned off is going to be of benefit in terms of energy consumption. So if you're in a hot and humid environment where you only want to try a 2-hour shutdown at night to see how everything responds, well, then give or take, and this is roughly linear, if you shut down for 2 hours, you should be able to save roughly 1/12 of the total energy that you're looking at over the course of a year. So keep in mind that the potential is certainly there, and it's worth thinking about and experimenting with in a risk-managed approach. And we'll kind of bump through this real quick. I think I already said all that. And the key here, I'm not going to go back through all of this setback and all the equilibration information, but we covered an awful lot of this in webinar 5, which was the June webinar a couple months ago. So if you're curious about the research and really what the numbers came out like, please do go back to that. But the thing to take away, by and large, is that materials react very slowly, especially in terms of relative humidity, to changes in the macro environment. Now, temperature changes, a book or archival material sitting in a particular storage area over the course of 8 hours might come to full equilibration with a one-time temperature change. But the thing to understand, or the thing to keep in mind, is that when we run a system shutdown or even a setback, it's not a one-time temperature change. We're not changing the set point condition. We're just doing less work, and that the environment within that storage area will slowly increase in temperature or decrease in temperature, depending on the season, will slowly increase in temperature over the length of the shutdown period. So the collection doesn't have the full 8 hours to equilibrate to the 2-degree temperature change. As that temperature slowly creeps up, the collection is going to slowly follow along behind. So maybe you see the full amount of fluctuation in the space after 8 hours, but the materials will not have caught up to that full amount of fluctuation in most circumstances from a temperature perspective. And usually where we find acceptable shutdowns, the amount of fluctuation in terms of degrees, I usually look for no more than 2 to 3 degrees Fahrenheit fluctuation over the course of a shutdown period. Those small fluctuations over time are typically what a mechanical system is going to control to anyway. Ask any facility manager, it's awfully hard to get a system to run tighter than plus or minus 1 degree. But that 2 degrees worth of fluctuation is fairly standard for operation anyway. We're just doing it on purpose, and we're doing it in order to save energy and realizing that there's very little preservation impact in terms of rates of decay as a result. Now I'm coming awfully close. I've got a few more slides here to deal with at the end. So I'm just going to deal with one or two of these case studies. I think I have 3 in here. But this is just an example for anybody who's thinking about this optimization work or energy savings in storage environments. This particular case in Washington, D.C. is a really good one. This is a library institution that called us up probably 5 years ago or so now, and they wanted to do some shutdown experimentation, and more than that, they wanted to go into a full optimization study of their preservation environment, their storage environment, and also how it is that mechanical systems ran. So we went in and went through, by and large, the process that we've talked about over the course of these webinars, and looked at the analysis and the data similar to what we've talked about today. And we found a couple of things. We did go in and implement the shutdown that they wanted to test out and experiment with, and we tried that and pulled the data and figured out that, all right, for some of their spaces, they could run an 8-hour shutdown without dangerous fluctuation. And for other spaces, particularly in the wintertime, we found out that they could run upwards of a 10 to 12-hour shutdown at night without seeing any significant fluctuation in temperature in the space at all. And by the way, in these cases, most of the time, if RH fluctuates at all, it's as a function of the temperature. So 1 or 2 degree fluctuation in temperature is not much movement in relative humidity at all. Now, the other thing that we found when we started to go in and pull the data from the mechanical systems and the loggers that we had deployed is that they were trying to dehumidify throughout the entire winter. And even though Washington, D.C. doesn't feel like Rochester in January, there's still no need for dehumidification in D.C. in the wintertime. So by correcting that particular behavior and looking at the shutdown, just those 2 strategies right there, just finding those 2 opportunities, came up with estimated savings for, and this is for one particular unit, and this is where the numbers get a little bit interesting. You know, we were able to save 31% at the supply fan in terms of how much energy the fan was using, 47% of the total energy used at the cooling coil, and 69% of the energy used at the heating coil. Notice that the actual dollar amounts look pretty small. And that's something that I want to caution you about as you start going in and thinking about this, is that, you know, this is not always a get-rich-quick scenario. This is something where you're trying to do a better job of it, and you're trying to be more efficient. And oftentimes, if you're working with a relatively small air handler in terms of the amount of air, cubic feet of air that it moves around, then the dollar numbers that you're looking at when you start achieving these savings aren't going to be huge. But the percentages are meaningful, and the lessons that we learned from this are really significant. And this is a case where this was one air handler that we were talking about. By looking and studying that one air handler, we realized that there were a number of other air handlers in the building that might be able to run with this same exact operation, with these that had these same problems with excessive subcool and reheat, and that might be possible for shutdowns. So now when you start applying some of these strategies to other air handlers through the building, those percentages are going to look fairly similar, but the dollar amounts, the actual dollar value, starts to become more meaningful and more significant. This one just very quickly because it's important. You run into a lot of zones out there where you have a mixed use zone and you're trying to figure out with a mechanical system, how do I manage a preservation environment that is in one room off of this air handler, and the same air handler is trying to control, in this particular case, a technical services division for a university library. All people, no collections, no preservation goal at all. So on one floor, that mechanical system is trying to achieve 60 degrees and a moderate relative humidity, and on the floor above it, it's trying to maintain 70 degrees. Now, what it comes down to is that means that the system all the time is going to have to cool in order to meet what needs to be done in the archives on the lower floor. But in addition to that cooling, now you have to reheat a portion of that air significantly back up to 70 degrees in order to achieve what the technical services space needs. And when you started looking at how it was heating and how it was able to cool to 60 degrees, you realize that this is one of those scenarios that the system just cannot efficiently achieve both of those missions. This is one of those cases where when you look at the mechanical system, yeah, there are some opportunities for optimizing. You can reduce energy usage in terms of looking at shutdowns and looking at slowing down the volumes of air that are moving around. But in the long-term scenario or in the long-term case, you're trying to do 2 wholly separate missions or 2 wholly separate mandates with one piece of equipment, and it can't achieve either one of them efficiently. This is one where, even though there were some ways to improve it, in order to really get to the best operation for both spaces in the long term, this unit needed to be split in 2. and it needed to have separate units managing both one for the archives and one for the occupied space. Now, balancing that preservation and energy reduction, this is just, when we start going through and thinking about what is the symptom that we see, if we're looking at a storage space, is it warmer than what we need? We want to go through and check, well, is the set point correct? How much supply, what is the supplier set point, making sure that that's appropriate? Did the reheat coil just go haywire? Is it making the air too hot? Is there heat coming in from an adjacent space? Or, in this particular case, do we have a blocked supply air path? This is something, whenever you see a particular portion of a zone or a zone going out of spec or out of set point, even though the system appears to be doing the right thing, check your airflow and go back up to the ductwork and start shining flashlights down these access hatches and make sure that you don't have some sort of obstruction somewhere within that air path that is keeping your supply air condition, whether it's cooling or whether it's heating, from ever reaching that downstream zone. If we've got high RH, too much humidity, watch the cooled air set point, make sure that the cooling coil is dehumidifying as well as it can. Make sure that you're doing enough reheat. Here's a key right here, and just to walk through these real fast, this is a cooling coil that's doing what it should, right? The cooling coil, we have cooled air getting down to 44 degrees to give us our 44 degree dew point, sent out to the space. We wind up with a PI 58, and all of our preservation conditions look really good. Now, what's going to happen if we go into this particular circumstance and realize that, we just messed up on the cooling side, and now all of a sudden our cooling coil doesn't have the same amount of capacity that it did before. Maybe we lost our chiller, maybe the chiller malfunctioned, or maybe we have poor flow through the cooling coil. So at the back side of the cooling coil, we wind up with 58 degrees. That's what's going to determine our dew point. Now we send that out at that 58 degree condition at 100%, and we've got this issue where by the time we get back out to the space, we see far too high of a relative humidity condition. Those storage spaces, if you see too much dryness or if the humidifier doesn't appear to be keeping up, watch for the set point on the humidifier, make sure that it is high enough. Check to see whether or not the humidifier is functioning properly. Unfortunately, humidifiers are a classic case of maintenance hogs. It takes an awful lot to keep them going over time, and it's not unusual to see malfunctions in one as they get older. Oftentimes, humidifiers are also a seasonal operation, so we see a lot of instances from institutions where it's seasonally turned on and off. In the spring, someone will go in and valve the humidifier closed, and in the fall, it's their job to go back in and open up that valve so that water or steam can get to the humidifier and work within the system. If someone forgets to open that valve, or that yearly preventive maintenance check is missed, then all of a sudden you can go for months at a time without getting any humidification. The other one is making sure that you don't bring in too much outside air. Finally, just looking at the effects of lighting on temperature, this is again why it's absolutely critical to make sure that those lights are turned off whenever possible. Here's a plot that shows very simply exactly what happens as a result of a light being turned on. These are occupied hours on the spikes. So on the weekend, when nobody's in there, the temperature drifts down. But when everybody comes in this case, here's a Tuesday morning, this is where the occupation starts. There we pick up a degree the next day, couple of degrees the next day, another degree. So the lights have a significant impact on the overall condition in the space. And if those are turned on all the time, imagine that instead of having these valleys where the temperature cooled down a little bit, we'd be running at the top side of this all the time and paying for it not only in terms of preservation quality, we'd lose a little bit there, but also in terms of looking at the total amount of cooling that the system has to perform. So the big ones at the end of the day when we're thinking about what these strategies need to be, we need to try and minimize that total airflow, whether it's through a shutdown or slowing down the fan. We need to try and subcool and reheat only when is absolutely necessary and looking at that dehumidification operation. I know there are a lot of system designs that I haven't gone through in this particular talk, Deskin system being one of them. And that's something that we'll get into in a little more detail hopefully in the future, but I do unfortunately am aware that we didn't have enough time to get there today. A big one in terms of looking at energy and looking both at energy and also at preservation quality is making sure that you minimize the outside air. We keep materials inside of the building and try to control the environment specifically because the outside air conditions most of the time aren't conducive to long-term preservation. So don't bring in any more of that outside air than necessary. it's more work for the system to do, and the more work that the system has to do, then the greater potential that more of that energy is going to get into the storage space where you don't want it. And finally, to minimize that lighting, try to decrease how much of it you're doing and make sure that whenever possible, just try to turn those off and save on both energy and preservation. Don't fight Mother Nature, right? Don't try to keep this flatline condition to 50% RH and 70 degrees Fahrenheit if the collection doesn't warrant it, if preservation doesn't warrant it. And what we've learned from research over the past decade, and what we've realized from practice and from just being in spaces and thinking about energy and operation over the past decade, is that 70-50 is not the best choice the vast majority of the time. And really, if you're going to spend your money to try and get a better preservation condition, and think about that carefully and critically over the course of the year. Don't spend money on energy to make sure that you're holding plus or minus 1 degree or plus or minus 5% or 2% relative humidity. You know, what we're learning is that for a lot of collections that we have in institutions around the world, that there's a little bit more leeway than that. We have a bigger spectrum that we can work within. So go broke, you know, spend your money efficiently and wisely trying to do better, but better does not necessarily equate, you know, very tight fluctuation control. And finally, oversizing equipment to quickly correct short-term variations in temper RH. As we said, in terms of rates of equilibration, the materials don't feel it that quickly, so it doesn't have to be fixed in 10 minutes or in 15 minutes or oftentimes even within 8 hours or 12 hours. The collection will coast along, and if there's enough material in a space, it'll help control that environment itself. So when you're looking at sizing or looking at equipment operation in the long term, think about this as sort of a, shall we say, a longer process. You know, not something that has to change inside of 15 minutes at a time. Finally, looking at next month, October 14th, we'll be back. I hope you can join us again. We're going to go through and just talk about sort of the softer side of this a little bit, looking at the strategy, looking at the planning, and talking about how we work through this in terms of, and this is a term that comes up again and again, but how to look at change management, how really to go in here and think about the process and think about what it takes in terms of effort and human activities to make some of these changes and work through this improvement and optimization when we're looking at preservation environments. Project website, as always. Thanks for joining us today. I will ask, please, if you get that email at the end of this, take a couple of minutes and send that survey back in, send that evaluation back in. We really do appreciate seeing them. It's a good opportunity for you to ask them additional questions if you have any that we can't get to. And we really, as I said, appreciate hearing from you, and NEH appreciates it as well. I will take about 5 or 7 minutes here and address a couple of questions for anybody that's interested in sticking around. I do honestly apologize for keeping you so long. There's a lot of material to cover today, and I hope I didn't bore you too much. We're going to expand this question pane, and Chris has sent a couple over. The first question comes in from Catherine Corman, and she's asking, how can you balance trying to minimize the airflow and the intake of outside air with the need to evacuate gases produced by decay? And the second part of that question is, how would you go about measuring the cleanliness of the air in the storage to see if the air is not getting too dirty? Catherine, you've just hit on a topic that is the, shall I say, the focus of a number of different studies right now, in terms looking at it from a couple of different perspectives. One is just how much do our materials actually off-gas, and how much of that off-gassing is, shall we say, of detriment to the overall preservation of the collection. That's one of the first parts, but the second part really is how effective is filtration, or how effective is air exchange in terms of removing some of those gaseous pollutants from the air, whether it's off-gassing or whether it's something that comes in from outdoors. Now, the first part of that is, I'm going to say, by and large, the jury's still out in terms of what the actual off-gassing limits should be for materials. There's a lot of discussion happening in the standards world right now, and there are a lot of research studies that are coming out currently, as well as just different, shall we say, real-life examples that are being given. And by and large, what I'm aware of and sort of what we work with here is the recognition that anything that is off-gassed out into the environment, first of all, one part is that as people, we tend to be far more susceptible or far more sensitive to those off-gas conditions than the collections actually are. And in that case, in this particular instance, I'm speaking directly to use a film collection that might be off-gassing acetic acid. The human tolerance level in terms of how much of that vinegar smell or vinegar syndrome we can take in a space is actually much lower than the threshold of the amount of acid in that particular circumstance that is going to impact or significantly increase the rate of decay for the rest of the materials. Which is, suffice to say that when we talk about filtering or air exchange in this case where we're off-gassing acetic acid, oftentimes it's more for human comfort purposes, and it has far less of an impact on the overall preservation of materials. The other thing that's been found, and this is a number of different studies coming out of Europe, I think we have some references online for this, but at least in the case of Denmark, what a number of people have found is that when we look at off-gassing, or when we look at what it is that is being given off within the preservation environment, oftentimes it's less the collection that is the culprit, and more the furniture or whatever materials it is that we're using within the environment for housing or as part of the structure itself. So the key there is to make sure that we're using low VOC or volatile organic compound materials, trying to reduce the amount of off-gassing that happens initially. But the other part of this is trying to take what opportunities we can to reduce the exposure of the collection to some of those pollutants that may get in. There's a big question in the field right now about how necessary it is to use gaseous filtration or gas phase filtration within a mechanical system. And more, those of us who are looking at it, and we're not doing a lot of the actual research here at IPI, but we certainly do run into a lot of the practical usage of it. More and more, we're moving away from using gas phase filtration in a number of different circumstances. One, if we can reduce the amount of outside air, we do reduce the vast majority of gaseous pollutant that comes into the space. Far more problems are created by ozone or by SO2 or NO2 that we bring in from outdoors than what are created by what we may off-gas from the collection or from the space itself. And second of all, there are different studies, and not to preempt things, but I think there's a study that's coming out here in October. I believe it's in Studies in Conservation, is the journal, where the researchers are looking specifically at the impact of pollutants or the question of gas phase filtration and how much we actually achieve with it. And that's something I think that we should keep an open mind to and realize that in terms of turnover, air exchange, fresh air need, it's certainly not as much as we've expected in the past. It's certainly not as much as what is required for human occupancy in terms of health and human comfort. And by and large, we haven't seen any instances in normal library archive scenarios where reduction in outside air has caused damage due to increased concentration of pollutants. So that's a longer conversation. I realize that might not have been the clearest answer. There's a lot going on there. But it's a good question, and one that I think that our traditional assumption of the amount of off-gassing is bad and therefore we have to use a lot of outside air to turn over the air and exchange the air is more and more being proven to be untrue. There's a second question here from Tara Kennedy. So what do these scenarios look like when you're using a desiccant dehumidification system? Thanks, Tara. Hopefully you caught the part where I said I realize I didn't cover desiccants in this particular talk. A lot of these scenarios look, what's the best way of describing this? Fairly similar. Okay, you have to be careful using shutdowns in a desiccant situation, primarily looking at the exhaust air that's coming off of the system. It is certainly possible to, when you turn the system off, if the exhaust air is able to condense, there's a possibility of getting moisture back into the air handling unit. That's a bad thing. But in terms of looking at shutdowns in the right scenario, you can certainly save an awful lot of energy both on the regen side but also on the wheel, both on the actual dehumidification and cooling side by shutting down and looking at shutdowns on desiccant systems. The other thing in looking at desiccant systems is how much of the air are you actually trying to dehumidify. One thing that we run into a lot looking especially at cold storage units, or shall we say cool storage units with desiccant systems, is that if you try to dehumidify the entire volume of air, you're going to spend an awful lot of money at that desiccant unit. Whereas if you apply the desiccant unit and the vast majority of your dehumidification to the outside air, or the biggest portion of the air where the moisture is coming in, it's oftentimes a far more efficient operation, and you get a lot more bang for your buck, if you will. So it's something to keep in mind. Desiccants are certainly a unique case. They don't all hold true to exactly what we just talked about in this particular presentation, but I think that's one that if you're dealing with that scenario and looking at desiccant dehumidifiers, it's worth a further conversation in terms of talking about how it is that you can look at optimization and energy savings while maintaining the same condition. All right, I have grossly gone over my amount of time, guys. Thank you very much for joining us today. We really do appreciate it. Hopefully this was helpful. If you have any questions, send them in as part of your evaluation, and look forward to talking to you again next month. Take care, everybody, and have a great rest of your Wednesday. Bye.